Welcome back, Rust Gang. If you're joining us for the very first time, my name is Bogdan and this channel is all about the Rust programming language. In today's video, we're continuing the Advanced Rust series by talking about advanced types in Rust. So with that said, let's get rusty. First, let's talk about the new type pattern. In the last video, we talked about the new type pattern in the context of implementing a trait on a given type. As a recap, in Rust there's a rule called the orphan rule, which states that you can implement a trait given type. As a recap, in Rust there's a rule called the orphan rule, which states that you can implement a trait on a given type if either the trait or the type is defined within your crate. However, if you want to implement a trait on if app, in Rust there's a rule called the orphan rule, which states that you can implement a trait on a given type if either the trait or the type is defined, which states that you can implement a trait on a given type if either the trait or the type is defined within your crate. However, if you want to implement a trait on a type where both the trait and the type are defined outside of your crate, then you can use the new type pattern. In this example, we want to implement the display trait on a vector type. However, both the display trait and the vector type are defined outside of our crate. We get around this by creating a new type called wrapper, which is a tuple struct containing vector. Because wrapper is defined within our crate, we can implement the display trait for wrapper. Then inside the implementation block, we can simply use the wrapped value, which in this case is a vector, by calling self.0. We can also use the new type pattern to increase type safety. Imagine you had two functions. One function took in age as a parameter, and another function took in an employee ID as a parameter. The type of both parameters is an unsigned 32-bit integer. If you want to prevent the user from passing in the employee ID instead of the type of both functions, one vector by calling self trait for wrapper. Then inside the implementation block, we can simply use the wrapped value, which in this case is a vector, by calling self.0. We can also use the new type pattern to increase type safety. Imagine you had two functions. One function took in age as a parameter, and another function took in an employee ID as a parameter. The type of both parameters is an unsigned 32-bit integer. If you want to prevent the user from passing in the employee ID instead of age, or vice versa, then you can create a new type which wraps an unsigned 32-bit integer. For example, we can create a tuple struct for age and ID. Then instead of passing in a raw integer to those functions, we can pass in either the age or the ID. Another use of the new type pattern is to abstract away implementation details. For example, we can create a people type which wraps a hash map of integers to strings. Code using the people type will only be exposed to the public API of the people type and have no knowledge of the internal data structures being used. In general, the new type pattern is a lightweight way to achieve encapsulation. In addition to the new line pattern, Rust allows you to create type aliases to give existing types new names. For example, here we create the type alias kilometers for a signed 32-bit integer. Note that kilometers is not a new type. It's a synonym for a signed 32-bit integers, so it will be treated just like a signed 32-bit integer. For example, here we declare x, which is going to be of type signed 32-bit integer, and then we declare y, which is going to be of type kilometers. Then we can add x and y because they're both technically the same type. The main use case of type alias y, which is going to be of type kilometers. Then we can add x and y because they're both technically signed 32-bit integer, and then we declare y, which is going to be of type kilometers. Then we can add x and y because they're both technically the same type. The main use case of type aliases is to reduce repetition. For example, imagine we have a lengthy type like we do here, used in many different places. Instead of writing this type out over and over again, we can create a type alias. Then we can replace all the long instances of our type with the type alias. Now this code is much easier to read and write. Type aliases could convey meaning as well. For example, thunk is a word for code that will be evaluated at some later point in time. This is an appropriate name for closure that gets stored. Next, let's talk about the never type. The never type is a special type denoted with an exclamation point, and in this case, it'll mean that this function will never return. Let's talk about why the never type is useful. Recall that in chapter 2, we built a guessing game, and we had some code which parsed user input into an integer. The code looks something like this. Inside our game loop, we took in a user input called guess, which was a string, and then we called trim and parse to parse it into an integer. The parse method returns a result type. If the parsing succeeded, we simply return the integer. However, if the parsing failed, we call continue to skip this current iteration. As you might have noticed, the type of guess is an unsigned 32-bit integer. So how is one arm allowed to return an unsigned 32-bit integer while the other arm ends with continue? As you might have guessed, continue has a never type. Rust will look at both arms of this match expression. The first arm returns a 32-bit integer, and the second arm returns a never type, so it can never return. Thus, Rust concludes that the return type of this expression is an unsigned 32-bit integer. We're allowed to write this code because if we get into the error arm, continue will not return anything. Instead, it will move control back to the top of the loop, meaning that guess will never be assigned. So the only type guess will be assigned is an unsigned 32-bit integer if we execute the OK arm. The never type is useful with the panic macro as well. For example, the option enum has a method called unwrap if we execute the loop, meaning that guess will never be assigned. So the only type guess will be assigned is an unsigned 32-bit integer if we execute the OK arm. The never type is useful with the panic macro as well. For example, the option enum has a method called unwrap, which will evaluate self, and if self is a sum type, it will return the value stored in self. However, if self is the none type, it will panic. Panic returns a never type. So if we get into the none arm, we won't be returning from this function. Thus, the return value of this function is t. One final expression that has the never type is a loop. Here, the loop never ends, so the value of this expression is the never type. However, this wouldn't be true if we had a break statement inside of the loop, because the break statement would cause the loop to terminate. Lastly, let's talk about dynamically sized types and the size trait. Dynamically sized types, sometimes called DSTs or unsigned types, are types whose size we can only know at runtime. One example of a dynamically sized type is the stir type. Here we have two stir types, S1 and S2. Now, because Rust can't determine the size of these stir types at compile time, if we try to write this code, we would get a bunch of errors. If I hover over S1, you can see that the error states, the size of the values of type stir cannot be known at compile time. All local variables must have a statically known size. So how do we fix these errors? Well, in this case, we already know what to do. Instead of using stir directly, we'll use the borrowed version of stir. This string slice structure will store two values, an address pointer the loop to terminate. Lastly, let's talk about dynamically sized types and the size trait. Dynamically sized types, sometimes called DSTs or unsigned types, are types whose size we can only know at runtime. One example of a dynamically sized type is the stir type. Here we have two stir types, S1 and S2. Now, because Rust can't determine the size of these stir types at compile time, if we try to write this code, we would get a bunch of errors. If I hover over S1, you can see that the error states, the size of the values of type stir cannot be known at compile time. All local variables must have a statically known size. So how do we fix these errors? Well, in this case, we already know what to do. Instead of using stir, we'll store two values, an address pointing to the location of the string in memory and the length of the string. Both the address value and the length of the string have a type of usize, meaning that we know their size at compile time, which is why this code works. In general, this is the way dynamically sized types are used in Rust. They have an extra bit of metadata which stores the size of the dynamic information. The golden rule for dynamically sized types is that we must always put them behind some sort of pointer. Here, the stir type is behind a reference, but we can also put it behind a boxmark. Trait objects, we mentioned that trait objects have to be behind some sort of pointer. Rust has a special trait called the size trait to determine whether a type's size can be known at compile time or not. The size trait is automatically implemented for every type whose size is known at compile time. Also, Rust implicitly adds the size trait bound to every generic function. For example, we have a function here which takes a generic, and Rust will automatically add the size trait bound like so. So by default, generic functions will only work on types whose size is known at compile time. However, you can use this special syntax to relax this restriction. Here we're saying t may be sized or not. Note that this special syntax is only available for the size trait. Also, because t can potentially be unsized, we have to put our argument type behind some sort of pointer. In this case, we've chosen a reference. That's it for this video. If you enjoyed it, then lean up against that like button. And if you want to see weekly Rust content, welcome back, Rust gang. If you're joining us for the very first time, my name is Bogdan, and this channel is all about the Rust programming language. In today's short video, we're continuing our series on advanced Rust by talking about advanced functions and closures. So with that, let's get rusty. We talked about passing closures to functions, but you can also pass functions to functions. This is useful when you want to pass in a function you've already defined instead of creating a new closure. To pass in a function as an argument to another function, we can use a function pointer, which is specified with the lowercase fn. If we hover over that, this is useful when you want to pass in a function you've already defined instead of creating a new closure. To pass in a function as an argument to another function, we can use a function pointer, which is specified with the lowercase fn. If we hover over this fn here, you can see it says fn is a function or a function pointer. In this example, we have a function called doTwice, which takes in two arguments. The first argument is called f, which is a function pointer with the following, which is going to be the argument passed in. And we create a new variable called answer, which is going to be equal to the return value of doTwice. And then we pass in add1, which is a of doTwice. We're going to call f with have6, a trait. So we can closures. There are three closure traits, and they are fn, fn mu, and if you were then 6 plus 6, which we're going to call add 1 with the argument 5, which is going to result in 6, then we're going to do that again. So we're going to have 6 plus 6, which is going to equal 12. So in this case, the answer is 12. Unlike closures, fn is a type rather than a trait, so we can specify fn directly instead of using one of the function traits as a trait bound. If you recall from the video on closures, there are 3 closure traits, and they are environment immutably. fn mu specifies that the closure captures the variables in its environment mutably, and fn once specifies that the closure takes owner closure traits. So if you have a function that expects a closure, you can pass in a closure or a function pointer, which is why it's best practice to write functions that accept closures. For example, we can update the f argument here to take in a closure or a function pointer by doing the following. First, we'll specify a generic, which is going to be t, and we'll say that f takes in this generic t type. Then we're going to introduce a trait bound. So we're going to say t is going to be anything that implements your trait bound rather than the lowercase fn, which is a function pointer type. This allows us to pass in a function pointer or a closure to our f argument here. This is a subtle difference, but now we're using the capitalized fn, which is a closure trait bound, rather than the lowercase fn, which is a function pointer type. This allows us to pass in a function pointer or a closure to our f argument here, and as you can see, our code still compiles. Do twice can still take in our add one function. One case in which you might only want to accept function pointers instead of function pointers and closures is if you're interfacing with external code that does not support closures. For example, C functions can accept functions as arguments, but the C programming language does not support closures. Let's look at another example where we can use a closure or a predefined function. In this example, we have a variable called list of numbers, which is a vector of numbers. And then we convert that vector of numbers into a vector of strings by calling the map function. Map will take in a closure or a function pointer that will be called for every element in the iterator. In this case, for every integer in our vector, we're going to call toString to turn it into a string. And then here we call collect to turn our iterator into a vector of strings. Currently, we're passing in a closure to map. However, we can pass in a function pointer like so. Here we're passing in the toString method on the toString trait, which will be implemented for any type that implements the display trait. Note that we have to use this fully qualified syntax because there are multiple methods named toString in this scope. Here's another useful pattern that exploits an implementation detail of tuple structs and tuple struct enum variants. Tuple structs use parentheses to initialize values inside the tuple struct, which look like a function call. In fact, these initializers are implemented as functions that take an example. Here we're creating a vector of statuses by calling map on a range of integers, passing in our value variant to map. Map is going to treat some people prefer a function pointer where the argument is going to be an integer and then the return value is going to be a value variant. Some people prefer this style, other people prefer using closures, but in any case, they both get compiled down to the same code, so it's up to your personal, is always a difference. The last thing I want to using closures, but in any case, they both get compiled down to the same code, so it's up to your personal preference. The last thing I want to talk about is returning closures from functions. Here we have a function called returns closure, which is always going to return the same closure. Closures are represented using traits, so we can't return a concrete type here. Instead, what we can do is integer and returning an integer. Took in an argument a, which is going to be in this case, if a is greater than 0, then we want to return a closure that will take in an argument b, add it to a, and then return the sum. Notice that we get an error here. If I hover over it, it'll say that no two closures, even if identical, have the same type. Consider boxing your closure and or using it as a trait object. As the error states, each closure is a unique type even if identical to another closure. The two closures we have defined here are different types, and the impl trait syntax only works if we're returning one type. In this case, we're returning one of two types depending on the value of a. So in this case, instead of using the impl trait syntax, we can return a trait object, some sort of pointer. In this case, we'll use the box smart pointer. And then we'll also need to wrap our closures inside the function body in a box smart pointer. And if you want to see weekly Rust, now as you can see, our code is compiling. That's it for this video. If you enjoyed it, then go ahead and tickle that like button. And if you want to see weekly Rust videos, then go ahead and subscribe and hit that notification bell. Lastly, and most importantly, I have a free Rust cheat sheet, which I would like to give to you. So if you want access to that, then head over to letsgetrusty.com/cheat sheet. And with all that said, I'll see you in the next one. What's up, Rust Stations? Welcome back.
But in theory, you could totally imagine. Welcome back. It's another Crust of Rust mini session. I really like that name. It's a good name. So we did the previous one on lifetimes, and in particular, sort of lifetime annotations and when you need lifetime annotations and when you don't. And result, okay. There's another question of like, what happens if here, like if they had a module called standard?
Okay, so this is me. I'm Erwin Raskoga.
This was very
I'm
nice.
14 years old right now.
Remove the other things
I actually have birthday in about 2.5 weeks.
But in theory, you could totally imagine that, like.
And I love programming as a hobby. And I also love creating compilers, fiddling around with custom programming languages. That's really fun. And I love birds. Okay, let's get into what are they? They're preprocessor directives. Maybe you've seen things like include in C programs. They look somehow like this. This is an example. Parameters, like in this case, circle area, takes a radius and squares it and multiplies with pi. This is a more complex example. It takes the same macros and it calls the macro. Macro calling looks like this. We just put the name. It looks like a function call, but it's actually replaced by the preprocessor. What do you think this is going to print? Now you don't have to pull out your calculator, the preprocessor. What do you think this is going to print? Now you don't have to pull out your calculators. This is the output. What do you think this is going to print? Now you don't have to pull out your calculators. This, if we add +2 in this position, it doesn't output what we expect it to output. And this is the first problem in this position. It doesn't output what we expect problem. If we add +2 in this position, I calculated the correct result, and it was 153 point to pull out. But there's a problem. This is if we add +2 in this position, it doesn't output what we expect. The correct result, and it was 100, and add plus the first 3 point blah blah, but it actually outputs 27.7. What's the problem in this case? What did we play? And we can fix this by just adding parentheses around. And this will +2. And simple. If we add +2 in this position, it doesn't output what we expect. There with. And I have another just adding parentheses around. And this will output the correct. And we can fix this by just adding parentheses around. And this will output the correct thing. And I have another exact adding parentheses around. And this will output the correct. And we can fix this by just adding parentheses around. And this will output the correct thing. Actually don't need it, but this is just for an example. The parentheses are placed correctly here. Everyone as before. It's 1 plus 2 times 2. So it will print 5. That's also not correct, because it should print 6. It will print 5. That's also not correct, because it should print 6. That's the second problem. As you can see here, this is what it expands to. 1 plus 2 times 2. It's also not correct, because it should print 6. That's the second problem. As you can see here, this is what it expands to. It's 1 plus 2 times 2. And that's of course wrong. Here, because it should print 6. Plus 2 times before by just adding parentheses around. Okay. It doesn't output what we expect it to output. If we add +2 in this position, it doesn't output what we expect it to output. If we add plus 2 in this position, it doesn't output what we expect it to output. And this is the first problem. I calculated the correct result, and it was 153 point blah blah, but it actually outputs 27.708. What's the problem in this case? Well, they're just simple strings, the output. If we add +2 in this position, it doesn't output what we expect it to output. And this is the first problem. I calculated the correct result, and it was 153 point blah blah, but it actually outputs 27.708. What's the problem in this case? Well, they're just simple string replacement. So if we look at what it replaces it with, it's pi times radius plus 2 times radius plus 2. And we can fix this by just adding parentheses around. And this will output the correct thing. And I have another example here, which is a very simple macro called sum. We actually don't need it, but this is just for an example. The parentheses are placed correctly here. Everything works fine, except for this. Because this is going to give us the same problem as before, it's 1 plus 2 times 2. So it will print 5. That's also not correct, because it should print 2. As this is going here, everything works fine, except for this. Because this is going to give us the same problem as before, it's 1 plus 2 times 2. So it will print 5. That's also not correct, because it should print 6. That's the second. That's also not 1 plus 2 times 2. Because this is going to give us the same problem as before, it's 1 plus 2 times 2. So it will print 5. That's also not correct, because it should print 6. So it will print 5. That's also not correct, because it should print 6. That's the second problem. And as you can see here, this is what it expands by the same fix as before, 1 plus 2 times 2, and that's of course wrong. And we can apply the same fix as before, just saying parentheses around here, and this works fine. This is what it expands to. And Rust solves all these problems. You don't have to think about string replacement. It correctly groups together expressions, so you never have these problems. But I actually experimented with C macros, and I found out that they can do some very crazy stuff. And this is valid code. Like this, and Copilot actually knows what I'm trying to do. This is valid code. I can run it. It outputs hello world. And if you don't believe me, I can change this here. And it still works. I look into this file, this is the entire macro thing. And it still works. I look into this file, this is the entire macro thing. I actually got that from Reddit, I think. It was in C++, but I copied it for C. It was a bit hard, especially with these things here, to correctly reduce a syntax tree, but it works. And I even prepared something more. Console error. Console reduce it. I copied it for C. It was a bit hard, especially with Reddit, I think. It was in C++. Reduce a I'll put just one single macro called function, which does all the things needed for this to work. Let's take a look at the hello world example. And this is using the bang symbol. This is the Rust hello world, and as you can see here, print line is a macro, and this bang symbol means that it gets called as a macro. If you don't have this symbol, it won't work, because the compiler will say, a print line is a macro, but you try to call it as a function. Now the thing is, in Rust, there are two types of macros. There are procedural macros, and there are declarative macros. And the interesting thing is, they're called both in the same way, both with name, then bang, and then an argument list. Procedural macros are basically a subprogram, so you write Rust code that gets compiled first, and then executed while compiling your program code, argument list. Procedural macros are basically a subprogram, so you write Rust code that gets compiled first, and then executed while compiling your program. The problem with this is that you have to compile code 2 times, which is slower than just 1 time. And that is what declarative macros solve. They're like function definitions, just a bit different. But they don't need a second compile cycle. They don't need a first today. That's a very complex thing. But what about declarative macros? Do they look like this? I'm going to call them macros. Okay, a very basic example. How do they look like this? You have macro rules, bang, say hi to. This is the name in that case. This is the argument list. And this is the content of the macro. And macro variables always start with a dollar symbol, then the name of this variable, colon, type. There are multiple types like expression in this case, or statement, visibility, attributes, all these things. And they're called like the print line macro using say hi to, bang, and then the arguments. The problem is they have to be defined before being used. You can have recursive macros, that works, because when calling, they're already defined. You can even define a macro above this, or below this. You can define a macro below here, call it in here, but it is defined when this gets inserted, because we call it already defined. You can have recursive arguments. The problem is they have to be defined before being used. You can have recursive macros, that works, because when calling, they're already defined. You can even define a macro above this, or below this. You can define a macro below here, call it in here, but it is defined when this gets inserted, because we call it below the definition of this other macro. And I have to apologize for my title. It just fits it so well. It should have been syntactically macro rules the world. It just fits it so well. It should have been syntactically macro rules the world. This was my title, macros rule the world, because that's true in Rust. And this would be syntactically correct. Do you see the difference between this? Just a few symbol class, and this would be syntactically correct. Do you see the difference between this? Just a few symbol class, but the other one would be correct. Okay, how are they built? This is macro rules, say hi to. In this case, this is the name. And this is the macro content. This is call signature, how it is called. And this is the body of the macro. And you can actually have multiple of these blocks, but I will get to that. Okay, a call signature. What is a call signature? It's basically a list of tokens. You need to use matching bracket pairs, which are parentheses, brackets, and braces. They can have patterns like we saw before, using $name, colon, type. And this is an example. It has to be called using this is an example, colon, expression, semicolon, expression. It has to be called using this is an example, colon, expression, semicolon, expression. Example, like we saw before, using $name, colon, type. And this is an example. It has to be called using this is an example, colon, expression, semicolon, expression. And every literal token, like in this case, this is an example, colon, and semicolon, they have to be directly inside you. And patterns can be like an expression or visibility or statement or whatever. And they can have multiple tokens, and they're correctly parsed by the compiler. It's a bit simpler than before. And this is the implementation. You see print line, blah, blah, expression times expression 2. And this is the implementation. If we change the signature to that, that's a bit simpler than before. And this is the implementation. You see print line, blah, blah, expression times expression 2. And we call it using 2 plus expressions, 2 additions. Rust correctly groups them together. We don't have the problem like in C, where it's just inserted, the simple text replacement, but it groups it like in C, where it's just inserted, the simple text replacement, which is like, okay, this call signature, can call this using this expression to addition inserted. Okay, there's more tokens. So we can say $parenthesis, then again some list of tokens or patterns, closing parenthesis, separator star. And inside, we can also do it the same way, $open parenthesis, content, close parenthesis, star. If we just try to use $item on its own, this will not work, because it will say variable still repeating at this step. That will be a compiler error. And you can actually use different kinds of brackets when calling the macro. You can use parentheses, you can use brackets, like in this case, or you can also use braces, these ones. This is also a very simple example, which just prints all the expressions passed inside here. Limited by comma, in this case, like you can see here, and any amount. A comma, in this case, like you can see here, and any amount. Here. Limited by comma, in this case, like you can see here, and any amount. Quickly, macro on its own. Now I thought it got the comma. This variable, if it looks like this, we can say petition verse will also work correctly. And then again, some list of tokens or patterns, closing parenthesis, separator star. And inside, we can also do it the same way, dollar open parenthesis content close parenthesis star. If we just try to use dollar item on its own, this will not work because we'll say variable still repeating at this depth. That will be a compiler error. This will not work because we'll say variable still repeating at this depth. That will be a compiler error. And you can actually use difference, or you can see here, and any amount quickly. But if we don't specify anything, the compiler will say it will not work because it will say expected end of macro invocation. If we want to have a trailing comma, this will also not work because this is where 0 or 1 are also called optionals come in. You can, instead of the star, you can use the question mark to say either nothing or the things inside the parentheses. Now, I talked about multiple headers before, or the things inside the parentheses. Now, I talked about multiple headers before. You can have multiple call headers in the same macro. You need them for alternatives. Rust macros do not support alternatives on its own. Like, you can say a repetition and then either this or this named with a colon some expression. And we print it using a equals blah and the expression. Or b and c. This is the other output. And another is basically that when we decide the macro, but in Rust we don't have this problem. Variables are scoped. And in this case, we cannot access number. It will say cannot find value number in this scope because the macro hygiene is defined outside of my function. We can solve it by passing an identifier token that's also a different token type. Correct in Visual Studio Code is pretty weird. It's very inconsistent. I tried some examples and sometimes it works, sometimes it doesn't really. It works very well at the call side. So if you like pass the step and you, for example, at line 25, this doesn't work in this case, but in line 33, this works fine. It's not as easy as with functions because they have to be pub is not supported on macros. And this is an example. I have a file macros.rs, the macro my macro, which takes two expressions and adds them and prints them. And this is the attribute called macro export, which is added to my macro. And in the main.rs, we can say mod macros, and just right after it, my macro blah blah. We do not have to import it because it's automatically imported if it's in the same crate. If you import something from a different crate, you actually have to add a use blah blah. Like in lazy static, I'm pretty sure you've already seen lazy static imports. It's a feature that basically works like functions, where you can say macro blah blah. So it's just like a function definition with functions. You actually use pubs, and it seems like it works so that the parser, the Rust program is parsed, then it's checked and then outputted, and the parser, which turns your text into the syntax tree, does some magic, and it basically inserts a placeholder in the position where you call the macro, and parses it later when he has the information from where the macro comes. And it can be exported and imported with pub and use. And this is a simple example with pub macro my macro. Just like with functions, the argument list, which is the same as the macro call header we saw before, and then the body which gets inserted. And this is the main file with feature. If we don't write as a command in the standard any amount of so-called comma this times identifier here, and this almost works now. We have a problem with this.
Motivating. W in the chats for Aditya over here. Thank you, Aditya. I think you only helped put all of this together. He's helped us throughout the filtering process, go through the code. Rust. Cursor or Visual Studio Code. Something like this. And if you've done C++, if you've done Golang, then you understand what this is. This is a main function. JavaScript, which looks a little different from other languages. How do you do it in C++ or JavaScript? You write function main, or you write int main in C++, right? And you return 0 over here. This is the return type of the function. This is what you're returning. This is similar. This is that you're defining a function. This is the name of the function. This is where you give the arguments. This is how you can give a return type. And this is a console.log equivalent. But is it? What is this? Is this a console.log equivalent? Is this a function call? Or is this a println. It has some weird, I don't know, something over here. So this is not a function call. Even though the first time you write Rust and you open it, you're like, there goes a function call. This isn't a function call. This is a function call. But as soon as you add an exclamation after this, it means it is no longer a function call. It is a macro invocation. It is a macro invocation. What does it mean for it to be a macro invocation? Macros pad rahe hain hum. What are we learning today? Macros. And the first thing we see when we initialize the Rust project, we see a macro. Why is this a macro? This is a macro because it is called like this. But what does it mean to be a macro? It means कि ये कोड कभी रन होता ही नहीं है. This code never runs. Let me take a screenshot of this and put it in Excel draw. Put it on the left. When I run the command cargo run, I see hello world over there. What does that mean? Does that mean this function was called? What happens when I open this function? I see something very complicated and weird over here, but it looks sort of like a function. Okay, maybe a function call, and there's another function being called over here called underscore print. Is that what is happening? When I run this, when I run cargo run over here, when I run cargo run in my terminal, does it mean that control reached here and then control reached, I don't know, here, and then this function got called? The answer is no. When you run cargo run, when you run this command, first a binary gets created. It gets built basically. It's like C++. If you've ever written a C++ project, what is the first thing you do? G++a.cpp-o/bin, something like this, right? You tell the G++ compiler to take the CPP file and spit out a binary. Is that true or not? That is how you compile a C++ project. This binary is what runs eventually. Same is true for Rust. You can also run cargo build first to create the binary, and then you can actually run the binary from ./target/debug/week1. That is another way to do it. You can run cargo build first to build the binary, and then you can run it. When you run cargo run, same thing is happening. First a binary is being generated, then it is getting run. But when you build it, this compilation step creates a binary, and then that specific binary gets run. And whatever, when this binary runs, hello world gets printed on the screen. There is one more step that happens between the final binary build and this Rust code. This Rust code getting converted to the binary. In दोनों के बीच में एक step और होता है. That step is macro expansion. I'm just calling it macro expansion. I don't know what it's actually called. But this code gets converted into a different code. And that code is what actually gets converted to a binary. You have written this code. The developer has written this code. But because there is a macro invocation here, पहले ये code एक और code में convert होता है. This gets converted into a different high-level Rust code. And that high-level Rust code eventually gets converted to a binary. So is this also compilation? Sort of. It's not compilation. It's macro expansion. The macros get expanded. What are we learning today? We are learning about meta programming. What is meta programming? It is programs that can write more programs. It is code that can write more code. What is meta programming? Code that can write more code. And what is this println statement? Println is a simple macro invocation or macro call that writes more Rust code. It doesn't get called at runtime. I repeat, this doesn't get called at runtime. At compile time, this gets expanded into something like this. And we can actually confirm that by running cargo expand. If you run cargo expand in your terminal, you will see it spits out something closer to what you wrote. It has a function name, but it doesn't have a println statement anymore. What does it have? It has this stdio and it expand in your terminal. You will see it spits out something closer to what you wrote. It has a function name, but it doesn't have a println statement anymore. What does it have? It has this stdio_print format args hello world. So your higher level code in Rust first got converted into other higher level code in Rust, which is what gets converted into a binary. So if you look at this println macro, यहाँ पे ये तो हो रहा था. If you try to read it, I mean, we'll get to this and what this are and what are these branches, but what this macro is saying is that if println is called with no arguments, then simply print /n, एक नई line डाल दो, add a new line. Or if it is called with some arguments, which this is where it gets really hard to read and write, कि हाँ ये arg:/tt, what is this, and what is this star over here and what is this dollar over here. But if there is some argument in there, then call the underscore print function, inside which you're calling another macro over here. You're calling another macro format args nl, and you're passing in the arguments inside. So this single line of code gets expanded into a lot of lines of code that you can see by running cargo expand. When you run cargo expand, you see this very big code. If I copy this, paste it here, these are the final set of steps that happen if you have a macro in here. If you don't have a macro, then this and this will look the same. There will be no macro. There will be a step of macro expansion. It will do nothing because there is no macro in here. But if there is even one macro or 5 macros or 20 macros, then this gets converted to this. This is what it's converted to a binary. That binary runs. That is the very first sort of explanation of what a macro is. It is similar to this being TypeScript code, which first gets converted into JavaScript code, which is actually what runs. This println is not a function. This never runs at runtime. Iska koi wajud hi nahi hai runtime pe. The binary doesn't have a println function. It has these, underscore print functions in them. It doesn't have this println function. Then what is the goal of this println function? It is to make development easier. It is to make so that the developer doesn't have to write so much code, because this is how you print something on the console in Rust. So do you expect users to write this? No, right? You expect users to have a high-level println macro. Another good question that comes at this point is, why is it not a function? Why is it a macro? Why can't it just be a simple function that takes multiple arguments? The answer is, we'll come to the answer, but basically this println function calls can get very complicated. You can pass in something like, you all guys already know this, but a variable over here. So if I write let x equal to 1, you can have 2 arguments, you can have 3 arguments, you can have 20 arguments. What you pass in this macro can get very complicated. When things get like that, when you are trying to almost call a function, but the inputs are very vague, they can be anything, is when you create a macro rather than creating a simple function call. When the input gets really vague, aapko nahi pata kya hoga, you don't know how many arguments there will be, you don't know the types of the arguments, they could be of any type, is when it makes sense to write a macro rather than writing a function. A macro runs at compile time, so you can do a bunch of checks for you at compile time, and a function of course runs finally at runtime, so it will do all your checks for at runtime. That's the very first explanation of a very first macro that we have seen, which is a declarative macro called println. And you can sort of start to read it a little bit. Thoda samajh aa raha hai ki if I don't pass anything, that probably this is what will come in the final Rust code. Let's try that out. I would expect that to happen. If I simply call println and do a cargo expand, what do I see? I see stdio format args /n, which was the very first branch over here. This branch gets called. But if I give it any argument, be it 1 argument or 20 arguments, if you guys have read regex in the past, if you know what regex is and how do you do pattern matching in regex, doesn't this look very similar? In regex, I think you have a question mark, or I think you have a dollar only, and star means that you can have multiple of these arguments, and this is the actual argument inside, and this is it needs to have a type or whatever this TT is. But can this be read, if you understand regex, can this be read as there are multiple arguments that can be sent, and we are just forwarding all those multiple arguments to a format args nl, which is another macro that does something with that. So if there are 2 arguments that I give to it, asd and a variable a, then these 2 arguments are what get forwarded over here to this other macro, so on and so forth. So that is the very first explanation of the first macro. We didn't need to go here. We were learning about traits first. But do we understand this? Do we understand level up below and look at what it expands to? But since we're going to write macros today, you need to understand what these are, what they do. Do we understand this? Are we good to go? All right. Simple enough. Okay, so we're going down. Agar yahan pe halat kharab hui hai, then things are going to get bad. So it's 91%. It's fine. See, I mean, in a live class, when I'm throwing so much at you, it is expected. Okay, some people don't understand. So take your time after the class. You know what to learn it from wherever. But make sure you learn or remember this by the end of it. All right. We're going to move on to the very first topic for today now, which was macros. Which was traits. Which is a very simple topic. You can build intuition for it really quickly. Let's say you have a struct called rect. I repeat, you have a struct called, you can build intuition for it really quickly. Let's say you have a struct called rect. I repeat, you have a struct, you can build intuition for it really quickly. Let's say you have a struct called rect. I repeat, you have a struct called rect. Build intuition for it really quickly. Let's say you have a struct called rect. I repeat, you have a struct, which is what would rectangle have? It would enough it and calculate that which input. This core as an input, and for each classes in JavaScript or classes in Java, you can run something like simple rectangle function that returns both of the adders, and there's a commenting of r.e self qualify cargo can it here, and I think it should be self-explanatory on in this case of that thing over here. R.area function don't care, you don't name. Another way to call a function on a struct. This is a static call. This is a static call. It is equivalent to if a function shape in a class can simply get calls to any instance signature. So if both of these, you want anyone, one does not implement the shape, therefore the error goes away. Beautiful. This is another way to print. If you want to debug, get user and get /user / scope. But basically, you can define a function below and use it over more Rust code, SQL, so on. So that's why you would want to use macros over functions in some specific. If you write, I repeat, if you write procedural macros, it's almost like writing a compiler for HTML, or if you write C++ for C++, or if you write SQL for SQL, so on. So that's why you would want to use macros over functions in some specific use cases. The downside of implementing a macro instead of a function is that macro definitions are more complex than function definitions, because you're writing Rust code that writes more Rust code due to this indirection. Macros generally are more difficult to read, understand, and maintain than simple function definitions. Another important difference between macros and function is that you must define your macros and bring them in scope. But basically, you can define a function below and use it over here, but you can't do that for macros. Macros should be defined above and used later on. You can't write a macro below and use it upper, which should be obvious if you understand how languages are actually run. When a language runs, it first creates a map of all the functions. So even if a function is defined at the end, it will be available. Versus macro expansion happens during compilation, where first the macro needs to come, then the invocation needs to come. All right. So that is what a macro is, and it is of 4 types. We've discussed this before. A declarative macro, print ln, simpler macro, only covers some use cases, will not cover extremely complex use cases like HTML. That are procedural macros can cover complex use cases like HTML or other things. Is of 3 types. Custom derived macro. And do we now understand why this is closely related to traits? A trait is something you write, and then you can implement that trait using a custom derived macro. As a developer, you can write the debug trait, and you can write the debug macro as well, so that other people can derive a default implementation for that trait. That is why these two are closely related. And then comes procedural macros, which are of 2 types: attribute like and function like. This and this are very similar. They look very similar. It's like you're calling a function. That is why it's called a function like procedural macro. An attribute like procedural macro, I already showed you. The get function that I wrote a while back. That would be a attribute like procedural macro. So if I press command and access, let me just write all 4 of them once in a single line. This is macro. Name string age function get underscore create underscore user exec values whatever you read it from the input somewhere from the arguments, and then lastly route get slash user slash or post endpoint, I would say. So hopefully you can read this. This is a attribute like macro, and this is a function like procedural. A function like procedural macro, an attribute like procedural macro, a custom derived procedural macro, and a declarative macro. Now, a function like procedural macro, an attribute like, and this is a function like procedural. A function like procedural macro, an attribute like procedural macro, a custom derived procedural macro, and a declarative macro. Now, question is, what is the difference between this and this? Both of them are functional. Why can't they be the same? And the answer is how they are eventually expanded. Declarative macros are a little easy to expand and are a little, it gives you certain things you can pass in. You can pass in, strings or expressions or types. Versus here, you can pass in anything as long as you can compile the final thing. Sorry, not compile. You can understand,
I had hardware, not hardware, like I think it fell down, so I need to take it to the I know, like to ask how to fix. So do you like this laptop? It's not bad, it's good. It's good, no? Is there any alternative? Actually, my start this job. So you are preparing for placements? No, I'm learning Rust, bro. So are you interested, like after the relocation, to stay near India, or you will go back to? Yeah, if I see a lot of money, bro, why not? Like how many rupees in rupees? How much money? 90 lakhs, 20 lakhs, 30 lakhs, 40 lakhs. What dream? See, if I see good one, if I see good earning, I will stay for maybe 1 year, then leave after 1 year. Great. It doesn't have to be much, but like I will just stay, work more harder. How much it takes, like to travel from your country to here in India? How much in one go? Like how many dollars? If you have like $500 to $600, yeah. Dollars. So that means like $500 means around 40,000 rupees in. Yeah, around 40K, 40 plus. Yeah. So what are you doing? Nothing, bro. Roaming here and there. Just came to check in what the students are doing. Are they preparing for the prom? Say I have been appointed as a chief official to that. See if people are studying for their placement or not. So what the fuck, bro? Yeah, I have responsibility actually. Are you sure? Yeah. Or you are joking? That's why I'm carrying laptop. So I'm noting down in the Excel sheet what are doing. So you are preparing for like week 1, so you are pretty probably. I'm not preparing for. So I will record it. I record it. I don't give a shit. Right. Click the photo actually also with this laptop. Yeah, I'm not sure. Someone who is studying in this. Great to know. Definitely. This is custom derived macro. This is declarative, and this is function like macro.
parse out the token. You can pass in anything as long as you can compile the final thing. Sorry, not especially custom derived procedure. A function like procedural macro, an attribute like procedural macro, procedural. A function like procedural macro, an attribute like procedural macro, a custom derived procedural macro, and a declarative macro. Now, question is, what is the difference between this and this? Both of them are functional. Why can't they be the same? And the answer is how they are eventually expanded. Declarative macros are a little easy to expand and are a little, it gives you certain how they like procedure macro. And this is a function like procedural. A function like procedural macro, an attribute like procedural macro, a custom derived procedural macro, and a declarative macro. Now, question is, what is the difference between this and this? Both of them are functional. Why can't they be the same? And the answer is how they are eventually expanded. Declarative macros are a little easy to expand and are a little, it gives you certain things you can pass in. You can pass in, strings or expressions or types. Versus here, you can pass in anything as long as you can compile the final thing. Sorry, not compile. You can understand, parse out the tokens, create the abstract syntax tree, figure out what your language is or whatever you expect to pass in. You can parse that over here and generate more code. Versus println or declarative macros are for simpler things. But you just have 2, 3, or 5 different branches that the user can pass. They can pass in a string, or they can pass in nothing, or they can pass in 2 strings, or they can pass in an expression, so on and so forth. If the user is passing in simpler things, then you would use a declarative macro. It's easier to write also compared to a procedural macro. If you want to attach an attribute like this to a function or a struct, or if you want to derive something on a struct or an enum, a trait on a struct or an enum, or if you want to write a function like macro, but this thing inside is very complicated, you need to parse it out to an AST yourself, is when you would use procedural macros. So what are the 4 types of macros? One is declarative macros. Simple, gives you a bunch of branches. Based on the branch, specific code gets replaced. Procedural macros, which is of 3 types. Custom derived, attribute, and function. Function wala is similar to declarative macros. Only thing is the developer gets more power on the input that is passed over here. Attribute macros, if you don't want to derive a trait, if you simply want to do something else, add some functionality to a function, to a struct, to an enum, then you use attribute like macros. Notice I don't write derive over here because I'm not deriving something. This is not a custom derive macro, which is the 3rd type. This is used when you have a trait and you implement you provide a default implementation of that trait. Do we understand various categories of this thing? Let me do a poll. If you do a poll and then we'll do, do we understand 4 types of macros? Beautiful. So then let's do 2-minute, chit chat, and then we'll move on to that. All the slides are just, sharing various types of macros. What is a declarative macro? For example, here I ask you to create a very simple eval declarative macro that takes some expression as an input, 2 + 3 × 5, and evaluates it. So what have I done over here? There will be an expression that will come. Just return that expression as such. So kya hoga? This will, just come over here. Let answer equal to 2 + 3 × 5. That will be 15. That's what gets printed. And this I've created a new vector macro, but vec is already a macro, right? You guys already know you can create. They have sort of vector like this. Let v equal to over here. I have done some a slightly basic implementation. It should be hard to read again. Okay, what is happening over here? Okay, there are multiple expressions that can be passed. That's probably what a dollar and a star means. Okay, there'll be multiple comma separated variables, which will be an expression. So that can be 1, 2, 3 like that. And we need to create a comma separated variables, which will be an expression. So that can be 1, 2, 3 like that. Okay, there'll be multiple comma separated variables, which will be an expression. So that can be 1, 2, 3 like that. And we need to create a temporary vector. We need to, for every, what does dollar back to star mean? Okay, for every x that exists, we want to push it to the vector and then we just return the vector. So right now you can add another one for an empty vector. Let's say, or more. The slides you can do it on your side as well. Inputs star x is multiple inputs. Want this macro to be replaced with? I will see. Let answer equal to all of this code, which is it's an inputs. Function call. You can invoke it however you want. Vector from here. That is the simplest declarative macro. Rarely do you write these. Most of the times you will write procedural macros. Any framework that you look at, Anchor. I have not seen Pinocchio, but I've seen Anchor. Most of the times you write procedure, write them. If you derive BOSH, serialize, BOSH, deserialize, you've probably seen this in the Solana world. If you've written any contract, so this is also a custom derived macro. It probably there is some serialized state that exists. So go read through them. To the docs, nothing crazy here. Attribute like macros. The struct. I want name to be placed with full name when I'm putting it in a table. Let's say there is another macro over here that is if I take structs. If there is a struct, does name now anchor macros are there are multiple writing the code. In our case, I mentioned you have to do it like this. BOSH does it the other way. It does little idiom. So 100 is what it does. But we want to do it this way. Any other questions? If there are, please ask. Finish this up. 5 more minutes, then we proceed. 2 people are on site here as well. I'm not trying to solve it. Yeah, A takes least significant, B takes most significant.
And to sort of continue this trend of focusing on a particular use case and trying to write like real code that needs this particular pattern, I wanted to take a look at declarative macros. So no like proc macros or anything like that. I have a video on that, but that is sort of a more advanced concept. Whereas here, because Crust of Rust is sort of intended to be like, let's deal with like one piece and just like do something with that piece and hopefully something that's understandable to a broader range of Rust developers. Even if you are a little bit newer to the language, like this is something that is really useful to know about. And so we're gonna be talking about macro rules, and Just before I jump in, I want to sort of point out, you can, if you like these videos, you can follow me on Twitter or YouTube or Twitch or wherever, and I'll, in particular on Twitter, post whenever I'm about to make new videos. Especially for Crust of Rust, I'll make sure to like announce them well in advance so that if you want to watch it, then you can just jump in. I will also upload all of these to YouTube afterwards. So I have a YouTube channel where I upload basically all the videos I do, both the longer sort of Rust live coding streams that are a little bit more advanced, but also these shorter Crust of Rust sort of isolated episodes. And the macro we're going to implement today is perhaps unsurprisingly also from the standard library. You'll remember last time we did this sort of stir split thing, which turned out to be something that was already in the standard library. And this was sort of by design because the standard library exemplifies a lot of real use cases. And so replicating things that are there is almost inherently going to be something that real people need. And I want to look at the vec macro. So you may have seen this either in the form of like declaring a macro, declaring a vector using the sort of vector literal syntax. But you might also have seen this version where you give some element that is clone, and then you say how many of those you want. And what this resolves to is a vector that has all those elements. Great. So what we're going to do is basically write this macro. So you'll see that this is sort of the general syntax of the macro rules, which is you say macro rules, and this is how you define a new macro. And the next thing is going to be its name. So this is how it's invoked, followed by exclamation point. And then you give a bracket, and then you give a bunch of patterns. So the patterns for macros they're basically they're arguments to the macro, but the arguments to the macro are much looser than arguments to a function, for example. Here, instead of having like a variable followed by a type, what you have is sort of a syntax pattern where anything that's variable, anything that's sort of provided by the user is going to be one of these dollar variables that has a type. And the type here is not a Rust type. It is a sort of syntax type. So this can be something like, it can be an identifier, it can be an expression, it can be an item, it can be a block. It can also be something like the name of a type, or the path to a type, or the path to a module. We won't dive too much into all of the different types here. What I want to teach you more about is like, how do you think about macros? What do they expand to? And sort of internally, how do they work? What do they do? And how can I write useful macros if there's something that I want to express? And we'll get to a bunch of this in the process of implementing vector. I highly recommend that if you're going to be writing vectors, take a look at the little book of Rust macros. This is just, it's a fantastic little gem of all of the weird little like oddities of macros. It explains a lot of the syntax, it explains many of the sort of quirks of it, but it also goes into a lot of really handy patterns. So if you see section 4 basically goes through, if you want to do something that does something like this, here's a pattern you can use. And we'll actually see some of that in our implementation of vec. Before we dive in, are there any questions about like what we're going to cover or the vector of vec? Before we dive in, are there any questions about like what we're going to cover or the vector macro in particular? Let's do that first. Dark theme for documentation. Yes, I can. Nice. If you just search for the little book of Rust macros, it should be the first result. I'm gonna keep that open over here. All right, so we're going to do the same thing we did last time, which is we're going to do cargo new lib, and we're going to call it vecmac, because why not? And we want just a dedicated library for this, in part because it's going to be easier to develop in isolation. You'll see this a little bit later, but also just because it's good to get into the habit of making libraries. So let me just construct a couple of terminals here for that, and dive into source lib. I'm going to get rid of these. And so we want macro rules. We want a vec. And notice here that I'm giving curly brackets for this. Macros are a little weird in Rust in that they have optional delimiters, not in the sense that you can omit them, but in that the caller can use any of multiple types of delimiters. So if we write vec like this, and let's say we just have an empty pattern, this is sort of the empty macro, then someone can choose to invoke it either as vec like this, or vec like this, or vec like this. All of these are valid invocations. You'll notice that like this on its own does not work. And to see why, let's try to run cargo check on this. All right, fine. Yeah, so this is fine. It expands to nothing, and nothing is allowed to be in these locations. And you'll see the Rust format actually changed these delimiters because it knows about the name vec. It knows that if you have it has basically hard-coded the name of the vec macro to say, always use square brackets for this. You'll see this if we define something else, like if we give it a different name, which we might want to so that we don't conflict with a standard library version. I wonder why the curly brackets do not need this. Then you see now it did not do that replacement because it doesn't know that this avec macro we've declared should probably also be formatted with square brackets. These are just optional, and you, in the current macro rule syntax, you don't have a way to say you must use a particular delimiter. Yeah, so we got a question about like sets and maps and stuff, and we'll get to that a little bit later in the stream. So when you write a vector, really what you're writing is a bunch of patterns over the input syntax. And one thing you need to know here is that the patterns are patterns over Rust syntax trees. They're not argument lists. So while you can do like arg1 is a type, arg2 is an expression, and arg3 is a path, right? You can do this, and notice now it says like we're missing tokens in macro arguments. You can totally express your arguments this way, but you don't have to. So in macros, you're allowed to introduce whatever you want as syntax. This might not be, yeah. Let's do this. I'm going to get rid of these because they're no longer that useful. So with this macro, I can give whatever syntax pattern I want here as long as that pattern is valid Rust. It basically means that you need to write a pattern where the input is like a syntactically valid Rust program. But that is the only restriction. Apart from that, the input syntax can be whatever you want, right? Like if I were to try to write something that matches what I wrote above, one example of that would be maybe u32 to x.foo semicolon standard path. Right? So you'll notice this compiles just fine. And this is not valid Rust syntax. If you try to compile this program, the compiler would go no, but it is syntactically valid. It can be parsed. And so all that matters for the input to a macro is that it can be parsed. And then what matters for compilation is whether the output is valid Rust. So the input has to be syntactically valid. The output has to be valid Rust because the output is what actually gets compiled. Basically, you can think of every macro invocation as being replaced by whatever this input was. When you're working with macros, there's a really handy crate. It's basically a cargo command called cargo expand. So you can install this with cargo install cargo expand, and then you can invoke it as cargo expand. And what it does is it takes as input the source for the crate you're currently in, and then it expands all the macros with their definitions. In this case, you'll notice if I run cargo expand, the output here is like it has the prelude. This is what Rust injects into every Rust program, but it doesn't have anything about our macro. And you might think this is weird, but because we have this here, but it's because the replacement is empty. We could try to make it not empty, right? So we could, for example, here say, let's get rid of this pattern and say that it's going to be ident. So ident is an identifier, and now we could say type arg2 is equal to arg1. Now this no longer need a semicolon, and this now needs to be identifier. So like also u32. This no longer need a semicolon, and this now needs to be identifier. So like also u32. And you'll see that if we now run cargo expand, this type alias actually gets included in the output because that's what the macro expands to. So any questions about like macro pend also u32? This no longer need a semicolon, and this. See that if we now run cargo expand, this type alias, we haven't actually written anything that's specific to vec. This is more talking about what macro rules even does. When you say syntactically valid, do you mean it is valid Rust grammar or just valid Rust tokens? It has to be valid grammar. So this is why when I tried to use a single arrow here, it told me that I'm not allowed to have a type token followed by arrow. And this is basically because the Rust grammar does not allow that particular pattern. And there might be good reasons for this, right? It might be that that introduces some kind of parsing ambiguity. And that's why that particular syntax is not allowed. And so you can choose what you want here. In fact, here, as might actually make a lot of sense. Right? And you see the moment I change it to as, this invocation is no longer valid. Macro that was named like type that for macros is that identifiers you define inside the macro are sort of exist in a separate universe from everything outside the macro. So for example, if I did not take an identifier here, let's say there's sort of a default version of this, where this is just going to be also u32. So there's one version that does this. I may have to do that. Yeah, that's a bad example. Let's do this. So this in and of itself works. And if we run cargo expand, you see that it expands to type also u32 is equal to u32. But if I write something out here that's going to be an apply for types actually. Let me see. 2. So this is not going to take any arguments. So I'm going to use this macro, and then I'm going to say like x plus 1. If I try to compile this macro, and then I'm going to say 42. So this is not going to take any arguments. So I'm going to use this macro, and then I'm going to say like x plus 1. If I try to compile this, cargo check, you'll see that it says cannot find value x in the scope, right? Even though this macro defines x. And the reason for this is the identifiers in macro world are just completely distinct from the variables outside of macro world. So if I up here said let mut x is 42, and the macro tried to say x plus equals 1, this also would not work because the macro is not even able to name x in that scope. And this is where identifiers come in. So we can take like an x, which is an ident, and then use that here, and then think of this as like passing the name into this other universe. So now where the x that's here is this x, the name out here. And so this lets us cross that boundary, but you can't otherwise cross that boundary without explicitly opting into it. And this is one of the ways in which Rust macros are hygienic. They're not allowed to access things outside of their own scope, identifiers in particular. Great. All right. Hygiene is not actually going to matter for us in this particular instance, but let's do sort of test-driven development here again, right? We want empty vec is going to be the most obvious test we want. True for the vector that comes from the standard library, but we want to be able to use our own vector here. So let's start with no patterns. right? What happens if there are no patterns? Well, it's now telling us that our macro rules is invalid, right? It's basically saying I was expecting to see a pattern here, but there is no pattern. Arguably, this error message is really bad and it should tell us missing pattern. Instead, what it's really telling us is that it's missing a token in macro arguments. And the reason for this is macro rules itself is a macro, and it is expecting that between the open and close curly bracket, there's going to be patterns. So let's define one, right? So for the empty vector, this should be really straightforward. This should just be vec new, right? We also here want to macro use and macro export this. Macro export. Because we want anyone who uses our library to be able to call this macro. Macros by default are, think of this sort of like pub for a macro. Without this, the macro will not be callable from any other library that depends on our crate. And if we run cargo test here, you see that this test passes. And if we run cargo expand, it should be pretty obvious why that is. Cargo expand test. Ooh, that's a good question. Can I make it expand my tests without unit tests? It's a very good question. Maybe not. Maybe if I do tests? That's annoying. Fine. Let's just do this then. Expand. That's also fine. So you'll see that this function gets expanded to just vec new, which is what we expected, right? That's how we define our macro. Great. Very straightforward. Any questions about why this example works? So this is obviously a simple macro example. It takes no arguments and just produces a static value. But it's useful just to see that this does the right thing. X example. Yes, in the $X example we had before, when you pass in the identifier, when you pass something to a macro, when you pass an identifier to a macro, you're just passing sort of access to the name. You're not passing ownership. It's not like calling a function. You're not moving that thing. You're just giving the name away to the macro. And then what matters for the purposes of ownership is what does the macro, the code that the macro expands to do with that name. It might move it, but it might also not. Expand lib tests. I don't think that's going to do it. Oh, nice. That does work. Great, good call. Yeah, so this expands what we expected, and it seems like this is call. Yeah, so this expands what we expected, and it seems like this is relatively straightforward for people. All right, so this case is straightforward. Let's now look at something that's a little bit more complicated, right? So what we want here is one that has not an empty vec, but like single. So this is going to be 42. We want to assert that it's not empty, and we want to assert, in fact, we want to assert that the length is 1, and we want to assert that x0 is 42. And we immediately see that it's basically telling us this macro was not expecting anything. That's because we don't have a pattern that covers that. So let's add something like that. We can call it element if we want to be fancy. And it's going to be of type expression. So expression is anything that is an expression in Rust. And this is almost everything in the language that you can write inside of a function. Think of it as anything that you could terminate with a semicolon. And I guess, so we're going to add, it's going to take an E. Let's just call it, this is just a variable name, right? I guess we can call it element if we want to be fancy. And it's going to be of type expression. So expression is anything that is an expression in Rust. And this is almost everything in the language that you can write inside of a function. Think of it as anything that you could terminate with a semicolon, roughly. And what is this going to expand to? Well, these, I guess, mute. And we're obviously not allowed to use the vec macro in here. That would be cheating. We're going to say these is vec new. And then we're going to do these.push element. And then we're going to expand it to v. Right? So we construct a new vector, we push the one element we got, and this is just going to replace whatever the expression in here was. So this is going to expand to vs.push42. And then we're going to give back vs. But you see that it's complaining here, right? If we run cargo check, so element, and what is this going to expand to? Well, these, I guess, mute. And we're obviously not allowed to use the vec macro in here. That would be cheating. We're going to say these is vec new, and then we're going to do these.push element, and then we're going to expand it to v, right? So we construct a new vector, we push the one element we got, and this is just going to replace whatever the expression in here was. So this is going to expand to vs.push42, and then we're going to give back vs. But you see that it's complaining here, right? If we run cargo check, cargo test, it says macro expansion ignores token vs and any following. The use of avec is likely invalid in expression context. It says something about let expressions in this position are experimental. It's clearly not very happy. And the reason for this is that what we've told Rust to do here is we've told it that this expression expands to these 3 statements. And that's not something you can do in Rust. You don't even have a way to write what this expands to in the language. Let's see what cargo expand gives us. Might not even give us anything reasonable. Yeah, you see here, it expands to just vec new and then nothing more, but it includes like the let here. This is clearly not okay, right? Like you can't have equals let mute vs. That makes no sense. Really, what we meant to do here was we meant for this to be a block. And inside that block, we can declare variables and write other expressions, and then the final value in the block is what gets returned. And so this is why in many macros you'll see this sort of double curly bracket. And it's because the outer curly bracket is what the macro rules syntax requires us to do. It's just to say this is the chunk of things that something expands to. And the reason it has to do that is because you might want one call to a macro to expand to many items, for example, like multiple functions or modules, in which case you don't want it to be a block. So you don't want it to default to produce a block, but you need the delimiter to be able to say all of the stuff in here. In this particular case, we do want it to expand to a block, and that's what this additional curly bracket is. Okay, so let's take questions on that before we move on. So does this roughly make sense why we need this extra curly bracket? Can you use a macro call inside of the macro? You can. There are some sort of weird rules around there, but in general you can. How is the macro rules macro implemented? So the macro rules macro is, as far as I'm aware, not a normal macro. It is basically a procedural macro, sort of. And you can sort of see this immediately, right? We don't have a way with the macro rules syntax to have this representation. We don't have a way to say that we want an identifier followed by curly brackets, because all of the macros we define using the syntax turn into something that you have to call with delimiters immediately. So we couldn't even write this syntax using macro rules itself, and you need to drop to something like proc macros. Should the no argument version of the macro use double braces, or doesn't it matter? Yeah, so this version actually doesn't need the double brace. And the reason for that is this evaluates to a valid expression. You can think of it this way: without the curly bracket, what's between here is not a valid expression. It is in fact a sequence of expressions. And that's why you couldn't use it in expression context. Basically, where the Rust compiler is expecting an expression, you can't put all these three things. But you can put this. In some sense, you can think of it as we're expecting the output type of this macro to be an expression, because we're expecting it to be used in expression context. Like the caller is going to place it where an expression would normally go. And this conforms to that. This is an expression, but these three lines are not one expression, and so therefore would not work in that context. Whereas with a block, this becomes an expression. Still coming. Yeah, so there's a proposal for a new version of macro rules. And I think the idea is that it's just going to be called macro or macros, that is going to allow you to... It's going to be a more powerful version with slightly different guarantees about things like hygiene, and that are going to work a little bit better with the module system and with use statements and stuff than the existing macro rules. But they can't really change macro rules because a bunch of code relies on it. So it's going to be a new macro basically for defining macros, declarative macros as these are called. How does the square brackets work in the instantiation? They're not referenced in the macro definition. Yeah.
Electron is still the most popular framework for building desktop applications, but a lot of people really hate Electron apps, and there are some really good reasons for that. It uses a lot of resources and the app sizes are huge. What makes Electron apps so popular though is the fact that you can simply use web technologies to build one desktop app and use it on every major platform. But while Electron has been mostly uncontested in recent years, an alternative promises to solve at least some of those problems. Tauri is a somewhat new framework for building desktop applications with web technologies. It promises to be small, fast and secure. And as all of that sounded too good to be true, I decided to build my most recent application with both Tauri and Electron. To find out if Tauri really has, so we can simply reuse the tracking project SolidTime. We wanted a web-based desktop application, so for my open source time tracking project SolidTime. We wanted a web-based desktop, and this is probably the main reason why Electron is so popular in the first place. Time. Instead of only make development faster, but it also saves users Rust, which is a in development time. Instead of JavaScript as a backend, I do not know Rust, but Tauri provides a lot of JavaScript APIs. At least that's what people were saying online. And when functionality, you should be fine. At least as well. So as long as you don't need a lot of backend functionality, you have ever been wrong. The SolidTime desktop app will mostly send API requests to our REST API, so we don't need any fancy data handling on the backend. Let's start with the set frameworks. Pretty straightforward. The story is first party tool, which proved to be a good decision, as a which I have honestly never heard before. One of the first features that our desktop app needs is a way to log into an existing SolidTime account. To authenticate our desktop app from our web app, we'll use something called deep links, which I promise has nothing to do with selling illegal application. So instead of HTTP, we can have our very own SolidTime application. Like with any other, use those parameters. Now, all of this hates developers. Registering those protocols does not work in development mode with both Tauri and Electron, because the app would have to be bundled and signed first. But that's my fault for taking a bite of the forbidden fruit inside of Apple's walled garden. For Tauri, there's a plugin to handle deep links, and in the most recent version, they even made the plugin first part working, because, well, so I can just listen to the deep link right from the front end. And this is Tauri's approach to a lot of standard functionality. The Tauri team seems very much aware of the fact that a lot of people do not want to write Rust code, and provides more and more JavaScript. Linking is simply an exact handling for different operating systems, and don't have to worry about any of that, because the plugin handles platform-specific behavior, and there's only one packaging tool. Another thing that you do have to worry about when using Electron is how to send the authentication tokens from the backend to the frontend. Because while both the backend and the frontend are powered by JavaScript, for security reasons only the backend has access to certain features. And if you want the system to send events. And let me tell you, setting up and sending those events made me feel like I'm in Java boilerplate code hell all over again. To pass an event from the script basically defines your API. Listen for the depload script just to emit and write your own abstractions to make it. Made me want to send an event script all the way to the other window. And one event listener, providing a much smoother experience. Place is because this goes for STEM desktop application time entry management validation custom window, and for Tauri just drag the entire window. In Tauri, this does unfortunately not work by default on the first click if a different window is focused at the time, which is, and it is also the window that you have to add a new permit. It took me buried since then. It's small. You will find obviously has a huge. The tooling I ended up using is actually Electron package and distribution solution, all sorts of distribution. Electron operating systems and developers in general are developers who use a platform that is not a Mac. Tauri's build system unfortunately does not support
In this video, I'm going to show you how to make your Rust APIs 10 times better using Java and apply sheet. And we are building Path Map Manager useful, a constructor function idiomatically named new, the unlock and lock methods, a method to list path.
Actix Web is widely regarded as web framework above many of today's more popular backend web frameworks. You might think you need to concede to a poor developer experience in exchange for Actix Web's great performance. It actually turns out to be very developer friendly, just as much so as today's other popular frameworks. Let's look at how to build a simple task management web service using Actix Web. Users can submit tasks to the service and query for their state. This pattern can be useful for many business applications where a user submits some asset or specification, maybe a 3D scene, waits for some process, like a 3D render, and expects some output file when the task is complete, like the rendered image of the 3D scene. We'll manage task state using an AWS DynamoDB table. So the first thing we're going to do is create the project. We're going to call it Actix Web Task Service. Now let's open that in our IDE. So the first thing we're going to do is set up our folder structure, and I'm not saying this is the optimal way to do this for a REST service, it's just the way I chose for this project. But we're going to have, inside the source folder, we're going to have, of course, main.rs, and we're also going to have a model directory, and these will be Rust modules, an API directory, and a repository directory. So repository is where our kind of interfaces for our dependencies are going to go. Model is where the model for our APIs is going to go. And API is where the appropriate value. Oops. To pass shared data in, to get it injected to all your handler functions, you need to use the data